In this problem, the work we do for part A is also going to help us answer part B. We're given a position function, and we're given a velocity function, which is to say that we're really given a parent function and its derivative, because velocity is the derivative of position. Then they ask us, when does the position switch direction? That's like saying, where does the parent graph have a max or a min? So an equivalent question would be, where does the velocity graph cross the x-axis? Because where the derivative crosses the x-axis is where the parent function has a max or a min. So we need to set the velocity function equal to 0. And that will get us critical numbers for where the velocity might have actually crossed the x-axis. So I'm going to set v of t equal to 0. And notice there is an e to the negative t in each term. I'm just going to factor that out, which will only leave me with cosine t minus sine t. That's my velocity function with e to the negative t factored out. I'm going to set that equal to 0. And now using zero product property, I can say either e to the negative t has to equal 0 or cosine minus sine has to equal 0. Well, e to the negative t is like 1 over e to the t, because a negative exponent gives you a reciprocal expression. Notice that there is a 1 in the numerator. You're never going to have a fraction equal 0 if the numerator is 1. Because in order to have a fraction equal 0, the numerator has to be 0. So we can kind of throw that out. Let's just work on making cosine t minus sine t equal 0. Or better yet, if I add sine t over, I end up with cosine equals sine. If you think about a unit circle and look for where cosine and sine have the same values, it occurs in the first quadrant, because in the first quadrant you're moving right and up, which are both positives, positive directions. Halfway through the first quadrant at pi over 4, cosine and sine have the same y value. When you get to the third quadrant, it happens again, because in the third quadrant you're moving left and down. Those are both negative directions, so sine and cosine are the same halfway through the third quadrant, which is at 5 pi over 4. And we can stop there because our interval is just one time around the unit circle. So if I plot my critical numbers on this interval, I have pi over 4 and 5 pi over 4. And I need to pick a number from each section of number line to plug into the first derivative, the velocity, and see what the sign is, positive or negative. So I could use like pi over 6 to represent a number on this first section of graph. Look, I know that e to the negative t is always going to be positive, because 1 over e to the t will always be 1 over a positive number. So I don't even really care about that. That's going to be positive no matter what. If I plug pi over 6 in for t, cosine of pi over 6 is square root 3 over 2. And sine of pi over 6 is a half. Square root 3 over 2, take away a half, is greater than 0. So in this section of graph, your first derivative is positive, meaning your parent function is increasing. Now I could use like pi over 2 to represent this middle portion. Cosine at pi over 2, that's the north pole on the unit circle. The cosine value is 0, the sine value is 1, and I get a negative result. And then I can use, for instance, 3 pi over 2, the south pole of the unit circle, to represent this last section of graph. At 3 pi over 2, the cosine value is 0, and the sine value is negative 1. 0 minus negative 1, of course, gives you a positive result. So we can see, since the derivative changes from positive to negative at pi over 4, the particle will start moving backwards at pi over 4. And then we can piggyback right into part B. When does the object switch direction and begin moving to the right? That occurs at 5 pi over 4, because v prime is positive from 5 pi over 4 till the end of the interval. Our justification here is that v prime is negative on pi over 4 to 5 pi over 4.